Good morning and good afternoon, my Algebra 2 students. Hope that you're all having a great day so far. And today we're just going to start on the S3 notes, continuing our discussion about sequences. And today's set of notes is really just putting all of the math into action. So you'll notice that the notes have a little bit more words to them today. It's just story problems essentially, but picking out what type of family we are, if we're arithmetic or geometric, and then how those lists would work, and being able to use the recursive and the explicit formulas that we discussed in the S2 target is what this particular goal is all about. So real life situations, and some of these problems are kind of interesting. So without further ado, let's go ahead and jump right in. Question number 1. If we read that here, it says an insect population is growing in such a way that each new generation is 1.5 times as large as the previous generations. Now suppose that there are 100 insects in the first generation. That's really important there. How many insects will there be in the 5th generation? So the first thing we have to realize is that when it says 1.5 times as large, we are dealing with a list that is geometric. So we multiply each number of bugs times 1.5, times 1.5, times 1.5. So that's a geometric type of list. The second piece of information that's really valuable is that it tells me A1, the first generation, right over here. A1, the list starts off at 100. So we could, if we wanted, write out the list and figure out the first number, the second number, and the third number. But ultimately, we're going to be accountable for figuring out A5. How many bugs in the 5th generation? And so we need to know how to land from here all the way over to there. And the explicit formula, if you recall, does exactly that. The explicit formula teleports us to wherever we want to go. So in a way, this becomes a question from the S2 target. What is the explicit formula for a geometric sequence? Well, it starts off with AN equals. That's where we want to go, ultimately. We need to know what we're starting with, which is 100 bugs. And because it's geometric, we're multiplying. Now, the value that we're multiplying by is 1.5. This is one thing to note. The same thing as 150%. We're going to get into percentages here later today, but 150% is the same value as 1.5, 1.5 times bigger. After that, we need n minus 1 as our exponent, and now that we have the explicit formula all set up, we get to go ahead and test out and find A5. So A5 is equal to 100 times 1.5, and then we have 5 minus 1, making a 4 as our exponent. So 1.5 to the 4th power. Okay, so this is where we have to go ahead. We pull out our calculator, and we're just going to type in exactly what we need. So if we have graphs up, we can just do second quit, and that clears it out. If we have stuff on our home screen, we can just hit the clear button. So starting off with 100, then we can put our parentheses 1.5 or 150%, and raising that to the 4th power pretty easy with the exponent key. If we press enter, we get 506.25. And that's worth writing down. Now, you have to think about the context. Context is really important in these situations. These are about bugs, but it's the decimal that I'm more worried about. Can you have 506 and then a quarter of a bug? And it turns out anything that's living, you are not allowed to use a decimal place because you haven't worked your way up to the next whole amount of bugs yet. So I know this is greater than 506, but we do not round it up. We get rid of the decimal, which is called truncating. We're going to only keep the whole number in that situation. So it's not like a smashed bug or anything like that either. I get kids that try to think of clever situations to get that quarter bug. So ultimately in the 5th generation, there will be 506 bugs. And it is nice to give a little bit of a context to that, so you need a label. If you want to tell me it's in the 5th generation, that's fine as well. Okay, but this is what our answers will look like in this section. A number with a label. So let's go ahead and let's try the second question. A child building a tower with blocks uses 15 for the bottom row. Each row has 2 fewer blocks than the previous row. Suppose that there are 8 rows in this tower. Question A says, how many blocks will be used for the top row? So we need to know if there are 8 rows, we are being asked to find A sub 8. Okay, in order to get there, we're going to have to use the explicit formula, the one that teleports us there. Now, what type of a list and where does it start? So each row has 2 fewer blocks, tells me that this is arithmetic. The fact that it is 2 fewer means my difference, my common difference, is -2 every single time. The 15, that is our A1. A1 is 15, where I start my list at 15, and then I go 13, and then I go to 11, and so on and so forth. I don't care if you write the list out a little bit, but we need to ultimately get to the 8th row. So writing out our explicit formula, we'll start off with AN equals. We need to know where this list is starting. It's starting at 15. Arithmetic things have to be adding. And after we add, remember we have n minus 1 as a group times our common difference, which is -2. So now we get to go ahead and we get to plug in 8 as our n value. So it looks like this, 15 plus, if I have 8 minus 1, that makes 7 times -2. This is the same thing as saying 15 plus 7 times -2 is -14. 15 minus 14 is 1. So what is that? 1 tower? No. That is the number of blocks. So we'll label that as 1 block. And I suppose that should make a good amount of sense. If you're building a tower and you got like the first row, the next row above it's going to be a little bit smaller, and then a little bit smaller, and then ultimately up there at the top you got that one block sitting on top. Okay? Now, the total number of blocks in the tower, which is prompt B, this is actually a sneak peek at where we are potentially headed. S4, the S4 target, talks about totals. Okay? The total just means we have to add up all the numbers in our list. So that would be 15 plus 13 plus 11 plus 9 plus 7 plus 5 plus 3, and then that final A8 is 1 block on top. So this is a pretty simple thing to type in your calculator. It might take you a second to get all those digits in there. But I want you to notice that there is a bigger pattern that can speed things up and essentially cut your work in half. So here we go on the calculator side of things. 15 plus 13 plus 11 plus 9 plus 7 plus 5 plus 3 plus 1. We should end up with 64 blocks. And it would be good maybe in this situation to say that this is the total amount of blocks, which is a little bit different. The answer before was in the top row. Now, what's the shortcut to this type of a situation? And actually, a very famous mathematician, I love this story. His name was Carl Gauss. So the story goes that Carl Gauss was in a one-room schoolhouse. So this is a long time ago. And his teacher was fed up with all the kids being super annoying that day. Probably had 3 weeks left in school, type of thing. And so she gave them a task that she figured would keep them occupied for a solid 30 minutes while maybe the teacher went out for a smoke break or just took a rest, So she tells all of her students in this classroom, you need to add up the numbers 1 to 100. So you'll take 1 plus 2 plus 3 plus 4, and you keep adding until you get all the way up to plus 100 at the very end. And so all they had were their chalkboards, and so you heard they got the piece of chalk out, and they were writing things down and erasing and writing things down. But Carl he didn't really move. He sat there and he was thinking for a second, and it took him less than a minute to figure out the answer. He goes up, and the teacher was a little upset, why aren't you working on anything, Carl? And Carl says, well, I know how much it would be. And she's like, no, you don't. You don't know how much it would be. And he's like, it's 5,050. And she was astonished because that's how much the total did end up being, but he didn't really do a lot of math on his board, and he certainly did it extremely fast for being a really little kid. So what he discovered, interestingly enough, is that you can pair the different values up. So 1 can pair up with 100 and make 101. 2 pairs up with 99, but that still makes 101, and 3 with 98, and so on and so forth. And so when you get all of those pairs, it kind of cuts your whole group in half, so 50 pairs of 101. And he was smart enough that he could kind of multiply, and he said 50 times 101 makes 5,000 and then 50. And this was a brilliant way to break up the math problem. We can do that here. If we go ahead and look, we have 15 and 1, we have 13 and 3, and both of those total up to make 16. Same with that group, same with this group. And so if you ultimately just take 16 times the 4 pairs that we were able to make, you get 64 blocks as well. So those two match, but it's kind of a fast, interesting way to get that total. Again, not something that we're going to really test you on, but it is something that we could be stepping into if we get to S4 as our target. Let's go ahead and let's try the third question. Suppose your business makes a profit of $5,500 during the first year. If the profit increases 20% per year after that, will it represent an arithmetic or a geometric sequence? What do you guys think? One hint that I have for you, if you are going to circle one of these two options, is that things that deal with percent are not always, but they are mostly going to be geometric. Okay? Things that deal with business grow at rates where you need to be multiplying, and multiplying is a geometric idea. So we're going to write both types of formulas in this situation, and we're going to find the profit that we would make in the fourth year. So when it says both types of formulas, I'm talking about the recursive formula as well as the explicit formula. So we'll need those over here. Now out of the two formulas, we really only use the explicit to do anything. The recursive formula talks about the relationship that all the terms would have. So what are we given here? Okay, we know it's geometric. The list in this case would start off with 5,500. This first year's profit is A1. Okay, after that, we know the profit will increase 20% per year. But we would not want to take 5,500 and multiply that by 20. Let me show you what happens. Okay, if we times by 20, which maybe we thought that was 20%, this gets gigantic. Okay, some people will say, we need to multiply because 20% is 0.20. And you're getting closer, but if I take 5,500 and I multiply that by 0.20, we get a smaller amount. And the profit needs to be increasing, not going down. So weirdly enough, if we are growing by 20%, what that says is I have 100% plus 20 more percent. And as any person could tell you, that is 120% overall. What we need to do with this, though, is we need to change it back into a decimal. And so all we have to do is take the decimal place behind the 0 and move it 2 spots over to the left. 1.2 is the same amount as 120%. It's going to be growing because it's larger than 1, and it's growing at the correct rate relative to what the problem told me, 20%. So if we took 5,500 and we multiplied that by 1.2, we're going to have 6,600 as our profit in the second year. And then we can times that by 1.2, and the whole list works by just multiplying by 1.2 over and over and over and over again. We can even see that growing over time. So that geometric list starts at this 5,500, and my rate, my R, is equal to 1.2, or 120%. So let's take those two ideas and let's write out our formulas. The recursive formula starts off with an equals, and this one is talking about how we relate to the previous term, and so that's an minus 1. Now the previous term gets multiplied by our 1.2 amount, this common ratio. Now you don't want to make the mistake of putting n minus 1 on the recursive formula. Okay, n minus 1 is talking about the previous term. We don't need an exponent on here. The term we stand on is the previous term if I multiply by that number. What I do need, however, is this piece of information that I'm starting at 5,500. So maybe I'll go ahead and I'll erase this to give us a little bit of room. And I'll talk about A1 equaling $5,500. We have to know where we're anchored. That is very important. So the explicit formula, the one that's used more often for sure, starts off with an equals as well. But for this, I need to know the initial value. The initial value that I'm starting at is the $5,500. I also need to multiply by that 1.2 amount. But what connects to the 1.2 here is the fact that I will be doing that over and over and over again. So I have n minus 1 as an exponent. Now we get to go ahead and we get to figure out how much we will make in the fourth year by using this explicit formula. So that will say A subscript 4. And we actually already passed it on our calculator, so it's not too hard to find it manually. But if I wanted to find it in the 400th year, this would take a long time, typing it in and just hitting enter, enter, enter. And if you misclick, you're in big trouble. So the fourth year here will just be the 5,500 amount. 1.2 gets raised to the 4 minus 1 makes it 3 power. And so now I can go ahead and type that in. And it was actually the $9,504 that I passed along the way. So labeling this 9,504 and saying that is the profit in year 4 probably is a good idea. Okay, the more description you have, the clearer that answer will be for someone else who's reading into the situation. So the very last problem, problem number 4, talks about Alzheimer's, which I've had students in the past think that Alzheimer's, like they've never seen it written, but that it's called old timers instead of Alzheimer's, which I thought was funny. But that's a disease where you start to forget things and you can't always like walk or do things like that. It's kind of a sad disease. As you get older, people who are older usually will develop that. So it says, each year, the Alzheimer's Association expects to add 5 to the number of families it serves in central Illinois. This year, the association provides service for 32 families. So question A says, write a recursive formula for the number of families the organization expects to serve each year. Does this represent an arithmetic or a geometric sequence? And then why? Okay? So the type of sequence that we're dealing with is arithmetic in this case, and that is because we are adding 5 each year. So 5 more each year, 5 more each year. That follows a fairly arithmetic pattern. Okay? So we can go ahead and give that little explanation here. Arithmetic, because we add 5 each year. So 5 is the common difference. It's good to use academic vocabulary in these explanations too. Hopefully you can read my chicken scratch over there. So it says write a recursive formula. So we can go ahead and we can start doing that. An equals. And then recursive means how do things relate. So I'm showing the relationship between an and n minus 1. All we're doing to the previous term is adding 5. And I need to know where I was anchored. So the first year, I'm assuming, I guess it's the 32 families that they gave me extra information about. So A1 is 32. Okay, part B says write the explicit formula for the number of families that the organization would expect to serve each year. So the explicit is used to go to a specific location. That starts off with AN equals, but we need to know exactly where we're starting at, the anchoring value. So that will be 32. Because it's arithmetic, we are adding. We just have n minus 1 and then times by the difference, the common difference that we're expecting each year. So that's times by 5. Another way that you could write this if you wanted would be 32 plus, and then have the 5 in front of the n minus 1. Those are the same exact outcome. So then part C asks us to use this idea. So how many families would the organization expect to serve in the 20th year? So we're going to be finding A20. Explain which formula you use to determine your answer and why. So this is definitely going to be the explicit, okay? The explicit can get you to a specific term, while the recursive just shows how terms are related. It doesn't do much of anything else. So in order to find A20, we're going to take 32 plus, we have 20 minus 1. 20 minus 1 is just 19. And we're going to multiply 19 times 5. I took that whole equation and basically just wrote it down here, but used 20 in the place of n. So now we're going to go ahead, we're just going to do some simple algebra. 19 times 5 is 95. 95 plus 32 is 127, I believe. Now you could just type this in, or you could do parts of it. Okay, but we should get the same answer no matter what our method is. And now we just have to go ahead and label what's going on. So these will be 127 families. Answers that deal with the context need to have a label. Really, really important. Okay? So hopefully that makes sense. All right, let's go ahead and let's move on to the next page with question number 5. So this problem says that you are enlarging a picture to be twice its size. And we're doing that several times. Originally, the picture is 1 inch wide. So part A says, write an explicit formula to model the size after each increase. Does this represent an arithmetic or a geometric sequence? And then explain your reasoning. So maybe we'll do that here first. This is a geometric sequence since you are doubling the size of the picture each time, which is a multiplying pattern. Probably help if I spelled pattern correctly there. So the problem would like me to write the explicit formula. So we're going to go ahead and we're going to start off with AN equals. And the explicit needs to specifically start with the initial value of the picture, which is 1. Doubling it, so twice its size, meaning 200%, or just 2.0, means we could put a 2 as the base, and then we will have n minus 1 as our exponent. And again, this is the explicit formula. Now, if we go ahead and look at part B, how wide is the photo after the third increase? And you'll notice we put a little bit of emphasis there. What term are we actually finding in that case? So you have to kind of think about, we start with a small picture, we double its size, we double its size. We're not actually finding A3. So this is not A3, as we'll see here in a second, because that's only 1, 2 increases, and the problem specifically emphasizes that we want 3 actions to have been performed. So we are finding not A3, but A4. So you have to be careful on the wording occasionally. So in order to do that, we will use the explicit formula. Let me change colors here. And A4 is equal to 1 times 2, and then we have 4 minus 1. This is pretty easy to do. 1 times 2 to the third, which is 1 times 8. And so in the end, it will be 8 inches. So the trick in that question is understanding what they are intending by using the word increases. All right, with that problem down, let's go ahead and let's travel to number 6. It says the deer population in Pike County is increasing, and this year it was 1.025 times last year's population of 2,537 deer. So just to keep re-emphasizing, this decimal is the same as 102.5%. So you take the percentage and you would move the decimal 2 spots over. That's how you get the numeric value. So part A says, assuming that the hunters are taken into consideration in the given calculation and that the population increase will remain the same for the next few years, can we write the explicit formula, all right, for the sequence? Is this arithmetic or is it geometric? So the family that this would belong to would be the geometric family. Okay, usually percentages are. You can't guarantee that, but it's a pretty good bet. And so the explicit formula here, if we go ahead and write it out, is AN equals, we have the initial value of how many deer there are, so that is 2,537. We have the rate of growth, so that is the R, so R is equal to that amount, 1.025. We always want this to be the decimal value, not the percentage value. Very important. And then we have n minus 1. So it looks like in part B, we need to actually use this to find the expected deer population for the 4th year of the sequence. So this is actually telling us to find A4. It's not saying after 4 increases or anything along those lines. So A4 is equal to 2,537. I multiply that by 1.025, and I have 4 minus 1, which makes a power of 3. This again is just something we type into our calculator. So we'll turn it on here, clear everything else out. I think we started with 2,537 deer. We'll put that rate of growth in, the common ratio, and then our exponent, we're applying that 3 times. So we get 2,732.07. So let's go ahead and let's write that out. 2732.07. And actually, I think 15 came after that. But this is talking about the amount of deer. And if you remember the question from the front page on bugs, we cannot have a fractional or decimal amount of deer. So really it just kind of comes down to the whole number value. Even if this were really close, like to rounding up, so like 0.8 would round up, or 0.56 or 5 itself would round up, we do not round up. We just keep the whole amount because we are not up to the next whole animal yet. So that would be 2,732 deer in the 4th year. And you don't always have to give that extra little information, but it does help, okay? Makes your answer a little bit more meaningful. Moving on to the last couple of questions. So for a 403B retirement fund, Huck Finn decides to make an initial deposit of $50 and increase each monthly deposit by $5. So will this represent an arithmetic or a geometric sequence, and why? And then we need to explain our reasoning here. So I'll make sure I try to type this out so we can read it a little bit clearer. But this is an arithmetic sequence. and that is since you are increasing your deposit just by $5 each month, this is just adding, it's not multiplying. So part B is actually pretty tricky. It says that if Huck only makes $2,000 a month, how long will he be able to sustain this sequence on his paycheck? So we're really asking, when will the pattern pass $2,000? So this is a question that needs to find exactly where $2,000 would occur. So that means we need to use the explicit formula to do that. That can find a specific location. But we're going to be solving it a little bit differently. So let's talk about that explicit formula. So it starts off with AN equals. It has A1, and because it's arithmetic, we are adding. We have n minus 1 times D. So to break this apart, AN represents the total deposit amount. So that would be like saying, hey, the first month he puts $50 in, the next month he puts $55 in, the third month he puts $60 in, and it just keeps on growing. Every month he adds a little bit more, saves a little bit more. A1, obviously, is what we started with. And then D, this is the $5 that we increase each time we are submitting some money into our bank account, depositing that in. So for this problem, if we go ahead and kind of put it together with the knowledge that we know, we want to understand when we will pass $2,000. Okay? Usually we don't put anything over there, but the total deposit amount that we want to know is when we will pass that $2,000. So we're equal to the $50 that this started with, plus we do not know n. N is actually unknown because this will be how far into the sequence. When will we pass $2,000? And that is going to get multiplied by 5 for the $5. So if we need to solve this for n, we have some work to do to get some of these things out of the way. The first step would be to subtract $50, okay, and get that other number on the left. So we're at $1,950. That's equal to n minus 1 times 5. And we have a couple of ways to solve this. Potentially you could take 5 and distribute. I would prefer probably just to divide by 5 because those will cancel, and then we can divide by 5 over there. Now 1,950 divided by 5, let's go up over here, is 390, and that's not equal to n, but it's equal to n minus 1, and it's pretty easy to get rid of that minus 1 just by adding. Okay, and so that will be 391 is equal to n. But what does that mean? Okay, how do we interpret this? Well, n goes back to how often this deposit is being made. And so he's increasing the $50 each month. And so this first number is the first month, the second number is the second month, the third number is the third month. So it's going to take 391 months before he ever has to submit basically his whole paycheck to go into his savings. Now that's kind of a silly pattern to like absolutely stick to. At some point, I mean, you're going to have to save money for groceries and things like that. And so the pattern isn't sustainable, but if he absolutely held to it, he would be able to go 391 months before running out of money in his paycheck, essentially. Now, if you wanted to know how many years that was, okay, you just take 391 and you divide that number of months by 12. And so that would be 32 and a half years. Each month adding $5 more, each month adding $5 more. 32 and a half years from now, he wouldn't be able to do that anymore. But hopefully he'd get a raise, or maybe he'd retire. But that's a little bit besides the point. So the very last question, Miss Arnold is crocheting a blanket. If she's currently on row 57 and crochets 6 rows each night as she watches Once Upon a Time or a TV show, how many rows would she have complete after 2 weeks? All right, so this is definitely one of those patterns that is arithmetic. That's good to note. She crochets 6 rows each night, so that's adding 6, adding 6, adding 6. So that is our common difference. The 57 here, that is our A1. And then we're questioned about how much happens after 2 weeks. And so you have to do a little bit of converting here, since it's each night. The difference is framed in nights. 2 weeks is 14 nights worth of work, or 14 days worth of work. And so we're really going to be finding A14, not A2. Valuable to know. So now we can go ahead and we can use the explicit formula that will tell us exactly how to get there. And again, the explicit is the more powerful formula. You can get to a specific location. So that'll start off with AN equals, we have that 57 that we're starting with, plus, since it's arithmetic, we have n minus 1 times the number of rows we crochet each night, and that would be 6. So going ahead and putting in a sub 14, we have 57 plus, we'll do 14 minus 1, sorry that's so small, that makes 13 times 6. We take 13 times 6 in our calculator, I believe we get 78. So 78 plus 57 ultimately leads us to 135 rows. Fairly standard answer. We just need to know how to take the word problem apart and then put it back together into the formulas that are best for our scenario. So hopefully these notes seemed pretty easy. It's just pretty much doing the same thing that S2 asked us to, except that we have to, decode a word problem and pull out the important information. Be on the lookout for questions like number 7, where we are asked to actually solve. That's kind of a big deal. And then be on the lookout for conversions. That's the last thing that can sometimes trip us up. Those are 2 ideas that we finish the notes with that are fairly common. Tests and things like that like to do this. So hopefully that helped, and if you guys have any questions, feel free to reach out. Be happy to take care of any issues that you guys have. So hope you all have a great day, and we'll see you next time. Thanks, guys.